treatment as the chapter, I think chapter 20. So heat treatment is very important chapter. Actually, this should have been there in first 4 or 5 chapters in CSWIP, not the 20th. So I think that they should first learn this, then learn the other components like welding and all that. But however, CSWIP, I don't know, they must have had some reason to keep this at 20. So heat treatment given to a particular grade of steel or steel mix supplied should be shown in the material certificate, may be referred to as supply condition. So what happens is when the steel goes through the heat treatment cycle, usually in material certificate you can see the heat treatment, what is the heat treatment given to the material. I will show you one. So this is a carbon steel stainless pipe, seamless pipe, 8-inch schedule 80. Okay, so wall thickness 12.7 mm of 6 meters, 6000 mm is 6 meters, grade B. So is API 5L, PSL1, ASTM 106 grade B, and NACE MR 105. So it is also important NACE number. And this is hot finished. So this is what is already written in the MTC of the material, that this is hot finished. What other supply condition is written apart from this hot finished? I think that's it. It's only written here. So if it is semi-killed, fully killed steel or hot finished, what kind of heat treatment is there, then usually it is delivery status, and it is written here. So we'll see one more. So this is a hot rolled plate. You can describe the good. So this is a hot rolled plate. It is written as delivery condition. So what is this material? This is usually it's written in Russian. So it's ASTM A36 plate basically. So ASTM A36 plate, whereas in the hot rolled plate condition. Standard benchmarking product delivery condition is written as rolled. So this is as rolled plate. So this is one example. So let's begin. That introduction has been done. So welding inspector may need to refer to material test certificates, so must be familiar with the terminology used. That's why I showed few samples. If you want more samples. Okay, this one is Chinese, I presume, Nippon Steel, so Japanese. So this is a what is this? Yeah, S355J2M. So you can see that this is hot rolled steel plate. So the supply condition is very important, and that's what the chapter is all about. So the supply condition, you need to know what is this and what is the client required. To the chapter. So welded joints may be needed to be subjected to heat treatment after welding, PWHT. And the tasks of monitoring the thermal cycle, checking the heat treatment records are often delegated to welding inspectors. So they should know if there is an 8-inch pipe joint, how many sensors are required or heating elements are required. If it is a 16-inch, how many, 24-inch, how many, and so on. And if in case there is any plate to be done, how many, which side you have to keep, how many you have to keep based on the thickness. So heat treatment of steel, the main supply condition for weldable steel are as rolled, hot rolled, hot roller or hot finished. Plate is hot rolled and finished size and allowed to cool air in the air. The temperature at which the cooling finishes may differ from plate to plate, so strength and toughness properties may vary, are not optimized. So you, depending on if you keep it in the air to cool, if you keep it in air conditioning to cool, or if you will keep in in the wrapped condition under with thick blanket of wool, or fire blanket thick, so how it will be cooled, depending on that material property and metallurgy science will decide what material you will get. So it's applied to relatively thin and low strength carbon steel, thermomechanically controlled process, TMCP, and controlled rolled, thermomechanically rolled. So we will come across TMCP material when you are doing jackets or tubular structures, which are offshore structures. Usually they are using TMCP steel. So steel given precisely controlled thickness reduction during hot rolling with careful controlled temperature ranges. Finally, rolling temperature is also carefully controlled. That time you will get some steel called as TMCP. So it's applied to relatively thin and high strength low alloy steel. So HSLA usually used for offshore structures with good toughness at low temperature. So cryogenic steels, TMCP material used. So if you want an example of so you can see this TMCP material. It's welded with so many processes and different backing. So if it is a API 5LX52 in this category, and this is the component which we are welding in the jacket, that is either bracing TKY or butt joint for bracing. Usually used for boat landing and this kind of, and also jacket bracing are tubular, so they are used for TMCP material. Apart from TMCP, there is normalized to TMCP, all kind of WPs are there. So, but you have to understand the supply condition is important here, and the supply condition for normalized steel, normalized to TMCP, quench and tempered steel, and TMCP, all kind of supply conditions will be important during the welding qualification. So, apart from that, let's go back to our. So normalized after working, rolling or forging the steel to size is heated to 900 degrees, then allowed to cool in air in ambient temperature, which optimizes the strength and toughness and gives the uniform properties from item to item for a particular grade of steel. So depending on its plate or its tubular, whatever normalized, so it is heated to 900 degrees and allowed to cool in air. That you need to remember this, what is normalized. So it's applied to usually carbon, magnesium and low alloy steel again. So you can see it is heat taken up in 900 degrees, kept it for some time, 1 hour, 2 hours soaking time, and then slowly, gradually brought to cool in the ambient temperature. So what is quenched and tempered? After working the steel, rolling or forging the to size, it is heated to 900 degrees and cooled as quickly as possible by quenching in water or oil. So after quenching, the steel must be tempered, softened to improve the ductility as quenched steel. So you can see here, so it is taken up 900 degrees, then kept for some time, then rapidly cooled, and then again they take it up to tempering cycle, and then slowly it was cooled. So it is done 2 times. So rapid heating to soak temperature, then short soak time, and then rapid cooling by quenching in water or oil, and then reheating to temperature, tempering temperature, soak and air cool. Then comes solution annealing. Many times you will find solution annealed material requirement. So compared to controlled temperature TMCP and as rolled, hot rolling condition. So the temperature is actually taken into this kind of time. If you take a time and temperature chart, you can see the rolling period, how long it is for different kinds of steel. So here we are as rolled or hot rolled, and you have a TMCP. So that time the rolling process is longer. So hot or cold working steel, working to size, steel is heated to 1100 degrees after rapidly cooling it. After then that is how it is done. So come to solution heat treatment. In solution heat treatment, it is rapidly cooled by quenching in water to prevent any carbide or other phase formation. So the temperature will be taken up to 1050 degrees, then kept it for soaking, and then from there it is quenched in water. So you'll get a very hard kind of steel. So typical solution heat treatment, solution annealing appealing to austenitic stainless steel. So usually this is used for austenitic stainless steel. Okay. So usually if you see MTC of stainless steel pipe, you should see solution annealing there. Simply annealing after working the steel, either it's pressing or forging to size. It is heated to 900 degrees, then allowed to cool in a furnace to ambient temperature. This reduces the strength and toughness but improves the ductility. So this is also one more way, just annealing. So annealing is also done to carbon, magnesium and low alloy steel. So it's applied to carbon and low alloy steel. Then comes the PWHT. So with this we have finished the heat treatment for the materials. PWHT, post-weld heat treatment has to be, everyone knows PWHT as PWHT was taught earlier, but or must have seen somewhere, but let us learn it properly. So PWHT heat treatment has been to be applied to some welded steel to ensure that the properties of the weldment is suitable for the intended application. So the temperature at which the PWHT is usually carried out is well below the temperature at which the phase transformation occurs, but high enough to allow residual stress to be relieved quickly and to soften any hard regions in the HZ area. So note that the circumstances when the welded joint may be needed to be normalized to restore as toughness, these are relatively rare, and it is necessary to ensure that the welding consumables are carefully selected because normalizing will significantly reduce the weld metal strength. So the major benefit of reducing the residual stress and ensuring that the hardness is not too high for steel for particular service of applications are improving the resistance of the joint to brittle fracture, improve the resistance of joint to stress corrosion cracking, improve or enable the welding joint to be machined to accurate dimensional tolerance. If there is any requirement, for example, in equipments and machineries, usually it is done and then it is done. Usually it is very easy to do the machining. So because of the main reason for the benefit of PWHT is to reduce the residual stress, PWHT is often called as stress relieving also. So in PWHT thermal cycle, application of standard code will specify when the PWHT is required to give the first two benefit of above and also give guidance about the thermal cycle that must be used. So this is not left to the QC inspector to decide when he should do stress relieving and when it should not be done. It's supposed to be there in the PQR itself. So if any material is requiring PWHT, the PQR should be done such a way that the PQR is tested after the PWHT is conducted for that particular PQR, so that data is also coming into the PQR. So while looking at the WPS used, immediately you will know if you have used so and so PQR number, that means the material will require PWHT after welding. So to ensure that the PWHT cycle is carried out in accordance with the particular code, it is essential that PWHT procedure is prepared following parameters. So PWHT procedure is already made, and welding engineer always makes this, and it is reviewed by quality control people. So what should it have? It should have a maximum heating rate, it should have soak temperature range, should have minimum time at the soaking temperature, it should have maximum cooling rate. So these should be minimum it should have. Let's see each one after another. So heating rate must be controlled to avoid large temperature differences. So if you have a, let's say 100 mm and then you need to do the stress relieving, directly you should not take the temperature to 500 degrees, it should be taken in steps. So you should not do large thermal gradient. What is thermal gradient? Thermal gradient is when you will take the temperature, suddenly it will become a gradient. So within the fabricated item, you should take it slowly. So which will produce large stress, and it may need high enough to cause distortion and even cracking. So if you take the heating suddenly to that temperature, naturally there will be distortion. So to avoid that, slowly it has to be done. So application standard usually require control of maximum heating rate when the temperature is item above 300 degrees, because steel starts to show significant loss of strength above this temperature. So after 300 degrees, you will see that the steel is becoming softer and softer and begins to lose its shape and size. So that's why it is important to you will take it very, very normally. So are the more susceptible to distortion and if large thermal gradients. So that is why need to take care. The temperature of the fabricated item must be monitored during the thermal cycle by thermocouples attached to the surface at locations representing the thickness range of the item. By monitoring the furnace and the item temperature, the rate of heating can be controlled to ensure the compliance with the code requirement at all positions within the item. Maximum heating range rates specified in carbon magnesium steel depend on the thickness of the item but tend to be in the range of 60 to 200 degrees per centigrade per hour. The soak temperature specified by the code depends on the type of steel and thus the temperature range required, reducing the residual stress to low level. So carbon magnesium steel requires soak temperature of 600 degrees, whereas some low alloy steels such as chrome moly steel used in elevated temperature service require higher temperatures, typically range of 700 to 760. Anyway, just devised by the welding engineer. So soak temperature is an essential variable for the PQR, so it is very important it is to be controlled within the specified limits, otherwise it may be necessary to carry out a new PQR to validate the properties of the item. At worst, it may not be fit for purpose. So if there is any issue with the soak temperature is becoming longer, shorter, then it will override the requirement of the PQR. So new PQR will have to be done to justify what mistakes have been done on site. So soak time, it is necessary to allow for the welded joints to experience the specified temperature throughout the full joint thickness. The temperature is monitored by surface contact thermocouples, and it is the thickest joint of the fabrication that governs the minimum time for the temperature equalization. So typical specified soak time is 1 hour per 25 minutes of thickness, 25 mm of thickness. So this is like a thumb rule, but then welding engineer usually decides this. So cooling rate, it is essential for the control the rate of cooling from PWHT temperature for the same reason that heating rate needs to be controlled to avoid distortion or cracking due to high stresses from thermal gradients. So codes usually specify controlled cooling to 300 degrees centigrade. Below this, the temperature item can be withdrawn from the furnace and allowed to cool in air because steel is relatively strong and unlikely to suffer plastic strain, deformation or by any temperature gradient that may develop during that time. So what you will do, so 600 degrees soak time and then bring it to 300 degrees and then air cool it, that also you can do. Heat treatment furnaces. So many times what happens, furnace itself is made like a very big room in which if you say that PWHT furnace, then the PWHT company will come and make a big room and they will put a lot of heating elements in that and take the temperature to that level, and that in that room you can put, if you want 100 spools, 200 spools, you have to tell them how many spools you have for PWHT. So usually small spools you can do in a very big furnace instead of doing individual. So oil and gas fired furnace used for PWHT must not allow flame contact with its fabrication, as this may induce large thermal gradient. It is also important to ensure that the fuel, particularly for oil fired furnace, does not contain high level of potential harmful impurities such as sulfur. So depending on what fuel is used for taking the temperature up, you need to note that if it is using oil, if you are using some other means for heating, then you need to specify what heating you want, or you want by electrical method, that also you can say. Local PWHT, for the pipeline or pipe spool which is big in size, usually it is often necessary to apply PWHT to individual welds by local application of heat. So for this PWHT procedure must specify previously described parameters, like those 4 parameters which we had said here. Which are those 4? Maximum heating rate, soaking temperature, minimum time for soaking temperature, and maximum cooling rate. So with these 4 items need to be specified in that procedure. For this, the PWHT must specify, okay, width of the heated band must be within the soaking temperature range, width of the temperature decay band, that is soaking temperature to 300 degrees. So this is all must be mentioned in the temperature in the procedure. Other consideration are position of thermocouples. So for heating, thermocouples are required. This is called heating element. So where you will place it, and within the heating band and width and decay band. So this mention is should also be mentioned. So if the item needs support in particular way to allow movement to avoid distortion. So the commonest method of heating for local PWHT is by insulated electrical elements. So electrical mats are a very good way of heating. This is what we are using. So gas-fired radiant heating elements can also be used, but I think we are using mostly electrical mats which are ceramic in nature. So you can see this temperature decay band, heating band and temperature decay band on both sides. So weld seam is in dead center. With this we have finished the theory after PWHT. So I'll show you one such sample example, that how the pile head was having ovality after doing the PWHT. This was happening from the client side, not done from our side, but still you will see in and out straightness. Difference in the center there was some ovality noted because of that. So we have taken one dimension report for that. So let's see this few slides of PWHT items. So these are called PWHT machines. You can see that this is how they look. This is the recorder. So there will be a recorder on the top, and there will be the heating transformer and all, everything will be inside this box. There will be a lot of channels where you can connect these cables. These cables are connected to the heating element, and then they are connected to this machine which is connected to this chart recorder. So this chart will record the entire operation. So this is how the machine looks. These are the ceramic heating elements. These are like pads, and these are moving small ceramics which is kept together in form of a mat, and this is what is linked to the cable, and this is also put on the pipe or whichever joint you are going to do PWHT. And this is called as the furnace. So this is a makeshift furnace, which is, you can see the fire is inside this, which is used, this blower is being used to stroke the fire, and this is the completely covered furnace. Inside you can put as much smooth spools as possible, and then it will get PWHT done. So this is also another furnace. It is also, you can see it is covered with this rock wool insulation material, and there is a gantry crane here which can put the spools from the top. So this is how the welding which is covered. I don't know what the PWHT is going on here. Is it for valve, or is it for a strainer, or it's for what? But you can see how it is covered and done the PWHT. So usually this machine is very heavy. It has to be taken to the site wherever the PWHT is supposed to be carried out. And this, I told you, is the top loading furnace. You can see this giant pressure vessel will be done for PWHT in one time. And this is also one way of covering the PWHT, and then you can see all the wires going to the. Then this is the PWHT being done for the big